Hello everyone, and welcome to Robotics Today. My name is Luca Carlone, and I'm excited to introduce Davide Scaramuzza as our speaker today. Davide is a professor of robotics and perception at both the Department of Informatics at the University of Zurich and the Department of Neuroinformatics, which is joined between the University of Zurich and ETH. He's the director of the Robotics and Perception Group and is working at the intersection of robotics, computer vision, and machine learning. Davide has been involved in several projects that have pushed the boundary of robotics and drones, including the European project S-Fly, which introduced the PX4 autopilot and pioneered Visual SLAM for drones, and the DARPA FLA program. In 2018, his team won the IROS Autonomous Drone Race, and in 2019, it ranked second in the Alpha Pilot Drone Racing Championship. Davide has co-authored more than 100 papers, as well as the book Introduction to Autonomous Mobile Robots. I'm personally using his textbook for my undergraduate course at MIT, and I'm a big fan of his early contribution, including the omnidirectional camera calibration toolbox, as well as the one-point Ransack. So for his research contribution to vision-based drone navigation and event cameras, Davide has won prestigious awards, such as the IEEE Robotics and Automation Society Early Career Award, a Google Research Award, the KUKA Innovation Awards, among many others, including several papers, Best Paper Awards. Besides being a prominent figure in the robotics community, he has also been active outside the research community. For instance, he has served as a consultant for the United Nations after the Fukushima nuclear disaster. In 2015, he co-founded Zurich AI, which is today Facebook Zurich, which has developed the Visual Inertial SLAM system running on the Oculus Quest. And he was also the strategic advisor of Dacuda, which is today Magic Leap Zurich. Many aspects of his research have been featured in the media, including the New York Times, BBC News, Discovery Channel, IEEE Spectrum, Wired, and many more. Besides being a collaborator, Davide is a great friend and a mentor, and it's a true pleasure to have him as our speaker today. So Davide, the stage is yours.
Thank you very much, Luca. Thanks a lot for the great introduction, and also thank you very much to all the organizers for inviting me to this seminar series. So today I would like to talk to you about autonomous agile microdrones, perception, learning, and control. And basically I want to tell you the journey about navigating autonomously using only onboard cameras and computation. But before I start, I want to send my gratitude to actually all the PhD students, researchers, postdocs that actually contributed to the research I'm going to show you today. This is a recent picture of my lab. And below is all the supporting grants that have sponsored this research. So this research, the research I've been doing for the past, I would say 10 years, have been around drones. So I consider drones among the most challenging and as well as amazing robotic platforms, because they allow you to actually work on topics that would be otherwise difficult with other research platforms. But also because drones are about to change the world in different ways. So if you look at the recent report by PwC about the sectors of the market where drones are actually considered to have an impact for, at the moment, the drone market is valued at $130 billion, and the most profitable sectors are inspection, agriculture, transport, and search and rescue. However, when you look at all the current drone applications, you will actually realize that drones are not really autonomous, but actually 99% of them are controlled in all these operations by human pilots. And how does a human control a drone? Well, using a remote control and either under line of sight or using a video link with a camera that sends video streams in real time to some goggles. But then there is the other alternative way, which is less used still on commercial drones, which is by using an autopilot. And here, actually, most of the autonomous drones that navigate, for example, beyond the visual line of sight, still use GPS. But as you know, GPS doesn't work indoors, and it's also not a reliable service outdoors, for example, in GPS-degraded environments. So what is the alternative to GPS in this case? The alternative is to use onboard sensors. So there is, of course, LiDARs, and there are a few companies that are popping out in the market, like Exim Technologies from Vijay Kumar. They use Velodyne, for example. The problem with LiDARs is that they're still expensive, and still they are heavy and also power hungry, like 10 to 20% of the power to fly is actually consumed by the LiDAR. So there is another alternative, which is to use passive sensors like cameras. And this is actually the sensor that is the dominant one used by some companies already, like Parrot, DJI, Skydio. And the advantage of cameras is that they are cheap, they are lightweight, and because they're passive, of course, they are low power. And that's the reason why over the past 10 years, I've been working on vision-based autonomous navigation of drones. Now, one of the most important things I think that matter for us researchers is to find a passion that drives our research. So my motivation to work on autonomous flying robotics has always been to build machines that can one day be used to autonomously search and rescue people in the aftermath of a disaster. And I'd like to do this for two reasons. First of all, because I come from the center of Italy, which was a region that was mostly impacted by earthquakes in the past centuries. And the second reason is because I consider search and rescue robotics one of the toughest fields in robotics. And also another important thing to say about search and rescue robotics is that in this type of applications, it is very important to fly as fast as possible for two reasons. First of all, because any time wasted can be fatal for the victim. And second of all, by flying faster, drones can cover more search area within their limited battery life. And flying fast is actually the leitmotif of this talk, which is about agile flight. But before I go into the details of this talk, I want to tell you, I want to review a little bit the last 10 years progress on autonomous vision-based agile flight. So the first demonstration of autonomous goal-directed navigation of drones, so non-reactive, using onboard sensors and computation was actually done within the European project S-Fly, which I had the pleasure to coordinate. So there at that time, we were actually flying very slowly. Here you see Laurent Kneip, who is acting as a safety pilot in case something goes wrong, using a fishing rod to safely secure the drone. At that time, we were running the computation off board on a laptop computer that is placed on the floor of the gym. And we used an onboard camera that is streaming images via a 20-meter long USB cable. So that was actually the first demonstration of visual SLAM-based navigation of drones. That was between 2009 and 2010. Then what happened? In 2015, DARPA launched a full program on fast and lightweight autonomy using only onboard cameras and computation, which was called DARPA FLA, so fast lightweight autonomy. And I was also fortunate to be part, actually, in this program, in the team led by Vijay Kumar from UPenn. And within the FLA project, we demonstrated the first high-speed autonomous flight. Actually, high speed in this case meant up to 10 meters per second. Where do we stand today? So today, in 2020, autonomous vision-based navigation, we can say, has become now a standard tool in several products, such as the Skydio drones, the DJI drones, as well as in the NASA helicopter that has been just sent to Mars and is supposed to land there in February next year. So we are living actually very exciting times. But at the same time, as a researcher, we need to ask the question, what is next to do for us researchers? And I think that the next challenge for research is to actually make autonomous drones fly as good or even better than human pilots. Indeed, if you look at the performance of autonomous drones today, they are still far from the performance of human pilots in terms of speed, versatility, and robustness. So look at this video, for example. Human pilots take years to acquire the skills that you see in this video. And this actually raises the question, can we maybe build an alpha pilot that can fly drones as good or even better than human pilots? Actually, this is both my dream and the goal of my research lab. And if we are successful, one day I would like to be able to demonstrate a drone that can beat the best human pilot at the drone racing competition, as well as in acrobatic maneuvers. But you may wonder, why bother about agile flight? Why does it matter to us all today? So, well, if drones can fly faster, it means they will be able to cover longer distances. So if you think about the battery life of drones, drones at the moment are very limited by their battery life. So they can only fly for 10, 20 minutes, which basically restricts their use in many applications. By making them faster, the hope is that they will be able to fly longer distances in the same time. And this is actually, as you know, crucial for many applications that matter to us all today, like search and rescue, delivery, and inspection. But also there is an additional reason, which is agile flight is, in my opinion, a really difficult problem to solve because it raises fundamental challenges for robotics research in terms of perception, planning, and control. And after all, our goal as a community is to push the limits. And I think that to push the limits, we really need to work on really hard stuff. And so at my lab, we want to push the limits on vision-based navigation. And I think that agile flight is one of the most exciting, but also one of the hardest challenges for robotics for the next decade. Of course, there has been related work on agile flight, plenty of related work. Now, what is a very good exercise to do when you approach a new field, this is actually a message for young PhD students, is to try to plot all the research papers on several axes of research. And here I chose the axis of speed and agility on the horizontal axis, and I put on the vertical axis prior knowledge / or using external sensors. So if you look at the early works on agile flight, and here just to mention a few, I would mention the pioneering work by Andrew Ng and Peter Abil on using reinforcement learning for acrobatic helicopter flight. There is also the work by Bry and Nick Roy on flying a fixed wing in a garage, the work by Lupashin and Raffaello D'Andrea, Daniel Mellinger and Vijay Kumar. What the common denominator between all these approaches is the fact that basically they were, yes, very agile, but they used external sensors or a prior map. On the other side, more recently, in the past 5 to 7 years, we have witnessed the rise of onboard sensor-based autonomous agile navigation. However, if you look at the performance in terms of agility, this is actually smaller than the agility that can be reached using external sensors or prior maps. And where do we want to stand? Where we want to stand is actually here, basically at the bottom right of this plane. So we want to have a system that is super agile in the future and also uses as little prior knowledge as possible and only using onboard sensors. So that's actually the goal of my research and also what I think the goal of the community should actually move to. However, to achieve this goal, there are many challenges to work on. And here I would like to summarize the research challenges that I'm both working on, but also, the research field is actually working on. Last week, we organized the 6th International Workshop at IROS on autonomous agile vehicles, among which drones. And we actually identified that these are actually the key research topics to address at the moment. So the first research problem is coping with inaccurate models of the sensors, of the actuators, of the environment, and physics, also model physics. And here one solution is actually to, for example, tight coupling perception and action. So tight coupling perception and action is actually a solution to this problem, but it also becomes a new research challenge because how can you do it well? Another problem is to reduce latency, because if you want to fly faster, we need faster sensors and algorithms. And regarding also faster sensors, there is now a plethora of novel sensors like event cameras, focal plane sensors like the SCAMP that offer new opportunities, but also there are new actuators that actually promise to lower the time constant compared to standard actuators and also have much more efficiency and so on. Also, there is another big challenge, which is, if you want to work on agile robotics, it means you're going to destroy a lot of robots. And this is important, otherwise the field cannot progress. But now if you destroy, it means that your work is going to be very expensive and you're going to need a lot of engineers. And it's also very unsafe because you will destroy the environment and potentially also hurt yourself and your research. And so we don't want to do that. So there is also a need, therefore, to develop simulation tools that can actually reduce the simulation to reality gap. So the ideal, the dream of the research community at the moment is to be able to train as much as possible in simulation because it's cheap, it's faster and safer, and then deploy to the real world. But so that also means, in principle, we also need better simulation tools. So I'm also going to talk a little bit about that. So to illustrate all these challenges, I'm going to focus in this talk on 3 tasks that we're actually researching on. The first task is autonomous drone racing. The second one is autonomous drone acrobatics. And the third one is low latency sensing. And I'm going to talk, of course, also about event cameras. So let's start with autonomous drone racing. Before I start, a small preface. So all the things that you're going to see in this talk are done using custom-built quadrotors. So we build quadrotors. My PhD students are able to build quadrotors, and they're building them from off-the-shelf components. Also, what I want to point out is that our drones are fully autonomous and rely only on onboard cameras and computation. This means that we do not use any GPS, neither external sensors. Now, when it comes to visual units, so typically now we use an inter-real sense camera that provides both visual and inertial measurements. And we do now most of our processing on NVIDIA GPUs, either Jetson TX2 or the Jetson Nano or even Xavier. Here you see one of our most recent drones. By the way, you can see that the weight is a little bit less than 1 kilo. So basically less than 2 pounds. We have a maximum thrust of 70 newtons, and that means a thrust to weight ratio of about 7. That means actually this quadrotor can fly in principle as agile as a first-person view racing drones of professional pilots. Okay, so we really paid a lot of work in order to make sure that we could match the performance of a research platform with that of current entertainment platforms, if you want. So let's now move on to the first topic, which is autonomous drone racing. And I want to start with a video. So in autonomous drone racing, a drone has to navigate autonomously a race course that consists of several gates in the least possible time. What you see in this video is the performance of our drone in the 2019 Alpha Pilot Drone Racing Challenge, where actually we ranked second among 400 participants worldwide. What you can see in this sequence is our drone that was reaching peak speeds up to 5 or even 8 meters per second in some cases. Now, how does autonomous drone racing actually work? Autonomous drone racing consists of 2 steps. So the first step is to plan a global trajectory that minimizes the execution time from the start to the finish. So we call this minimum time global trajectory. The second step is to execute this optimal trajectory. And actually, as a matter of fact, executing the optimal trajectory as accurately as possible, by the way, is the hardest step, because any deviation from the optimal trajectory will lead the drone to underperform. Now, what are the main causes of these deviations? So the main causes of these deviations from the optimal trajectories are mostly drift in visual odometry, visual inertial odometry, and inaccuracies in our models of the actuators and of the environment. And because of this, it is very important to be able to constantly couple perception and control. This is often said at conferences, but what does it mean to couple perception and control? And why is it actually very important, especially for drones? In fact, it's less important for self-driving cars. Look at this very simple toy example. Consider this drone. Let's assume that this drone is a vision-based drone that is localizing itself with respect to some point of interest that are here denoted by the yellow star, okay? Now, if this drone wants to reach a certain goal position, this means that it has to point its thrust vector in the direction towards the goal. However, by doing so, it has to rotate. And now what happens is that by rotating, basically it loses the visibility of the point of interest, of the features that it was using to actually hover, okay, if the task was to hover. So, so to solve this issue, we need to create a synergy between the perception and action loops. So we need to do what we call perception-aware planning and control. And this is super important. We humans do this all the time. When you grab a cup, when you pass through a door, we do it all the time. But it's less obvious for robots. And this perception planning and control coupling is even more important for drones because they rely on visual cues in order to navigate. Now, how can we solve this? So we have been working on this perception-aware navigation for quite a lot of time now. And one of the most important things, of course, is to be able to use a tool that can already bridge some gap. So we decided to actually exploit multiplicity control because it's a tool that allows you to bridge the gap between planning and control. What we actually did is that we adapted multiplicity control in a way to make it actually perception-aware. How do we make it? How did we make it perception aware? So what we did is that we combined some classical action objectives with some perception objectives. What are the action objectives? The action objectives are, for example, to follow a given reference trajectory and to stay as close as possible to it, as well as, for example, to satisfy the under-actuated system dynamics and minimize, for example, the actuator's limits in order to not saturate the motors. Perception objectives are, for example, to maximize the visibility of a point of interest. For example, if you navigate through a track in drone racing, you want to constantly look as long as possible towards the next gate. But also you want to minimize its motion blur. So there is something to also do on the image plane. So what we do here is that we define the perception objective. So in this case, for example, we want to minimize the projection of the center of a gate is distance from the center of the image, but we also want to minimize its optical flow speed, because by doing so, we hope to minimize the motion blur. Then what we do is that we assign a quadratic cost to these terms, and we add them to the optimization problem that we solve. And we managed to solve this in real time using Acado at 100 Hertz by exploiting real-time iteration, which is a tool that allows you to actually use intermediate approximations of the optimization as intermediate results, and then you start executing the trajectory already. By the way, we release the code open source, if you're interested. Now, if this is clear, how we solve the perception-action coupling, the next step in drone racing is to detect the gates. How do we detect the gates? So here, if you look at the state of the art, until the deep learning revolution, people were mostly using handcrafted gate detectors, for example, using HAUF or other special descriptors and so on. However, it turns out that for the task of drone racing, when you're flying very fast, you need something that is much more robust. So we actually opted for gate detection by means of a neural network. In particular, we devised a neural network that regresses for each frame the relative pose of the next gate together with its covariance matrix. Okay, so this task is done by a neural network. However, there is a problem. Collecting ground truth data for this task is very tedious, and as you can imagine, it's also very expensive. So indeed, training a network that can reliably detect gates can require, actually, in our experience, up to 50,000 images in diverse environment. So to facilitate this task, we collected data directly in simulation. And actually, we used Gazebo, and as you can see, it's non-photorealistic. Now, in order to allow transfer from the simulation to the real world, we use, in this case, domain randomization. Specifically, we randomized everything that we wanted our perception to be invariant to, which is, for example, the illumination. We randomized the background texture, the color of the gates, and also the shape of the gates. And thanks to this variability, as I said, it was not necessary to actually use a photorealistic simulator for the task of gate detection, though. Now, let's move to the real-world results. And this is already, I think, impressive to see that our policy training simulation was able to generalize already to an unseen real world, which is exactly what you see in this video. So what do you see here? So first of all, on the top left side, third-person view, you see our drone that is actually navigating a bit slowly here, a racing track. What you see on the right is actually what is happening in background. So you see in green, the predicted gate poses that are predicted by the neural network, together with their covariance, which is marked in purple. And you can see that as the network exits a gate, the covariance is actually pretty big because you are far away from the gate of which you try to predict the next covariance. But as you approach the next gate, the covariance shrinks, which is in accordance with our intuition. What are the red gates? The red gates define the prior map. So the point is that I didn't say, but basically we have a common filter that fuses optimally the information coming from onboard visual inertial odometry with the position of the gate poses coming from the neural network. And then we have the perception-aware model predictive controller that then executes the trajectory, making sure that at each instant of time, the quadrotor looks at the next gate. So it's perception-aware. What you instead saw on the bottom left video is basically the first-person view, and those three axes represent the projection of the relative pose of the gate into the camera view. Okay, now I want to move to another research topic that we're working on, which is how to perform autonomous drone acrobatics. So remember my big dream also, that was also to make a drone able to get closer to the performance of human pilots, also in terms of acrobatic maneuvers. And this is work that I did in collaboration with Vladimir Colton's group at Intel, and was published at RSS this year. What we showed in this paper is deep drone acrobatics. So we showed actually for the first time that a vision-based quadrotor that has only access to onboard sensing and computation is capable of flying acrobatic maneuvers with accelerations of up to 3G, which is actually close to what the best human pilots can achieve. Before, previous researchers had attempted to do these acrobatic maneuvers, but they only succeeded using either GPS or motion capture systems. So to the best of our knowledge, this was the first work that was actually done using onboard sensors and computation. Now, the traditional approach to control drones typically relies on the separation of state estimation, planning, and control. And this is not the approach that we opted for in this work. Why is that? So there are 5 reasons why we opted to do an end-to-end, to learn an end-to-end sensory motor control policy. And the reasons are the following. If you use the traditional architecture, you will notice that these modules, state estimation, planning, and control, are usually designed individually rather than conjointly, so by co-designed. And there is some problems with this, which I will say in a moment. Second of all, these modules run consecutively rather than concurrently, while we know that in nature, perception and action, as I said before, are actually coupled. And additionally, this modularity introduces latencies, by the way. Third of all, each module is sensitive to errors in their internal models of the sensors, of the actuators, of the environments, and of the physics. So this means that small errors in each module will affect negatively the performance in each of the other subsequent modules. Fourth of all, there is another problem, which is this architecture requires extensive tuning, especially for the control gains, especially at high speed. And this is actually much more relevant in the task of acrobatic maneuvers. And finally, fifth reason, it requires extensive expertise by the code developer, also called domain knowledge. And so to recap, all these problems that I mentioned so far actually are detrimental for very fast and agile flights, such as drone acrobatics. At such high accelerations, in fact, any small errors will lead to the unavoidable crash of the vehicle and therefore to its complete destruction, which we want to avoid at any cost, because it will also cost, by the way. This is the reason why, in contrast to the classical traditional control architecture, we actually proposed to directly learn an end-to-end controller in the form of a neural network. So basically, we have a controller that maps directly, a neural network that maps directly sensory inputs, such as images, inertial measurements, and the reference trajectory directly into control commands in the form of collective thrust and body rates. And I'm going to anticipate something, but what I will show in the results is that our end-to-end learned control policy actually happens to be more robust and more accurate than the classic approach. And this is actually interesting. Now, what we do in this paper is that we train our controller, our network, exclusively in simulation. And then we deployed it to the real world without any fine-tuning. So this is also called zero-shot learning. So why simulation? The reasons are several ones. So simulation is fast, it is cheap, and it is safe. Also, it does not require any human annotation, and it also allows the collection of almost unlimited amount of data in a pretty limited time. By the way, just for your interest, the training took about 5 hours on a normal desktop PC, but the inference on board the drone takes only 20 milliseconds. So we can actually run this algorithm at 50 Hertz on board the NVIDIA Jetson TX2. Now, it is important to point out that it was necessary to train in simulation, because if training was done from demonstration, as in previous works, then the data collection would have been very expensive, and also you're always bounded by the performance of the human demonstrator. However, now the key issue when you train in simulation is that there is no guarantee that the policy will also transfer to the real world. And this is because simulation and reality are still different. And this is actually called the sim to real gap. And this is due to the fact that we still don't live in the Matrix movie where everything is simulated. Now, this makes it necessary to therefore ask the question, what representation is best for reducing the sim to real gap? Raw image pixels or intermediate representations? And the answer comes from a Science Robotics paper, which I find very, very relevant for robotics research in general, that was published in Science Robotics in 2019, where they actually show in this paper that the current state of the art end-to-end approaches that directly map raw image pixels to control actions are actually significantly outperformed by approaches that use intermediate representations. In particular, what they show in this paper is that the neural networks that are fed with intermediate representations like segmentation masks, optical flow fields, depth maps, and so on, can actually train faster, achieve a higher task performance, and even generalize better to previously unseen environments. And for this reason, we decided in this work to opt to use an intermediate representation rather than to use raw image pixels. Now, when you do this, now the key question is, what is the best intermediate representation to reduce the sim to real gap for the task, especially of drone acrobatics? So the standard strategy to solve this issue is to reduce, is to match the observation models in simulation with the observation models of the real world as well as possible, which actually, in other words, means to make the simulation as realistic as possible. However, we took a different approach. Indeed, notice that our simulation environment, which is the one on the left, is gazebo and it's non-photorealistic. And it should actually, we want to transfer it to the real world, which is the image on the right. And so instead of trying to match the observation models, which we didn't, we decided to transform these observation models with an abstraction function that decreases the Wasserstein distance. So concretely, what we do is that we transform raw image streams into feature tracks, which we show transfer better between simulation and reality. And if you think about, it's in accordance with our intuition, because feature tracks appear not too different in a non-photorealistic simulator and in the real world, if you think about, right? Now, what we show actually that using these feature tracks, our learn policy can transfer from the simulation to the real world and can even generalize to different indoor and outdoor environments and also to different physical platforms, by the way. Now let's move to the architecture. So one particular challenge of our end-to-end approach was that the sensory inputs arrive at different rates. So to cope with this, we proposed an asynchronous architecture based on temporal convolutions. Now, what do we feed to our architecture? We feed the feature tracks given by the visual front end. So they are coming directly from the inter-real sense. Then we feed inertial measurements, actually in the form of integrated debiased measurements. And we also feed a reference trajectory. Then what we do is that we keep a history of each input stream. And then at a constant frequency, we take the newest batch of each stream and we encode it using temporal convolutions. And then we concatenate all these encodings and we feed them to a standard MLP, multilinear perceptron, that basically outputs then, that produces the control commands. Now, what do we use for supervision? For supervision, we use a model-based model predictive controller, so an MPC. Basically, the MPC acts as the expert teacher. This teacher has access to privileged information, okay? And as a loss, we minimize a cost function that depends on the output control commands. Now let's move to the interesting results. So we evaluated the policy on 3 acrobatic maneuvers, which you see in these pictures, which are the power loop on the left, the barrel roll in the middle, and the Meti loop on the right. They will look similar to you, but they are not, in the sense that in each loop, actually the drone is rotating about the different axes. And it's also, in one of the loops, is also actually navigating backwards. And this is actually even more difficult for humans, but it plays no difference for an autonomous machine, by the way. We also have a 4th maneuver, which is the combination of all these 3 maneuvers. So it's at least 3-4 times longer than the initial 3 maneuvers. Now, let's move to the quantitative results. So the quantitative results were extracted in simulation, okay? You cannot extract them in the real world. So here you see the quantitative results that we started in simulations. On the left, you see the tracking error versus the maneuver time in seconds. And what you can see, so our learned end-to-end policy is in blue. You can see that our trajectory tracking error is much smaller than the one of standard MPC, so visual inertial odometry plus MPC. And that's already interesting. What you see on the right is instead on the x-axis, again, the maneuver time. And what you see on the y-axis is the success rate. Now, we count as 100% if the quadrotor successfully executes all the combo maneuver, which is basically the consecutive execution of all these 3 loops without ever crashing. And then otherwise we discount them proportionally. Now, what we see is that our end-to-end learn control policy achieves a 100% success rate out of 20. By the way, this was 20 trials. While if you instead take the visual inertial odometry plus MPC, so the standard traditional architecture, we have a success rate of about 90%. So it crashed 2 times out of 20. While what is in yellow? In yellow, we have our learned end-to-end control policy, however, with the assumption that it would only use inertial sensors and no feature tracks. And you can see that in this case, the inertial sensor alone are not enough to give the success rate. So it is important to use visual information. Now, what is the main takeaways of this research? The main takeaway is that the learned end-to-end control policy outperforms by up to 25% the traditional baseline of estimation and control based on VIO plus MPC. In particular, we show that our learned end-to-end controller can fly more consistently and more precisely and reduces the chance to crash by up to 25%. What we also can conclude is that inertial measurements play a more important role than visual measurements for short maneuvers, while for longer maneuvers, the more important is the role of visual information for reducing the drift, okay? And this is then, again, the results. Basically, in conclusion, our policy was able to generalize to different indoor and outdoor environments, but also to different physical drones. And I would like to add that thanks to this learned controller, we were able for the first time to demonstrate such agile acrobatic maneuvers all autonomously with onboard sensors and computation. And by the way, these maneuvers are also super difficult for human pilots, which take months to actually learn these maneuvers. So what are now the main takeaways of learning versus model-based controllers? So to recap, so far I presented 2 tasks, autonomous drone racing and autonomous drone acrobatics, which relied on different approaches. A model-based controller for the task of drone racing and a learning-based controller for the task of drone acrobatics. In this slide, I want to summarize the key takeaways for robotics research. So in contrast to model-based approaches, I think learning-based controllers are more robust to drift in state estimation, do not require any tuning, and are also very easy to code. On the other side, instead, I have to say that they offer poor generalization performance and also difficult to interpret. And this is a general problem in general with the networks. Therefore, I think that future research efforts should focus on how to best combine the benefits of these 2 worlds. Now, as you learned in this research, we used extensively simulation. What type of simulator did we use? We used actually a mix of Gazebo, Bullet, and a real engine, and we decided to actually gift this to the community. The simulator we use is called a Flightmare, and it was just released open source a few weeks ago, and it's basically a new photorealistic quadrotor simulator, so specifically meant for quadrotors, that is compatible with ROS, Gazebo, OpenAI, Gym, and Bullet. It provides interfaces for easy configurable objects, high fidelity sensor suites, 3D point cloud extraction, and it's also compatible with virtual reality hardware such as the Facebook Oculus Quest, which I think nowadays is also important to keep into account. So I hope this simulator can be beneficial to the community and can also incentivize the community to perform better benchmark comparisons and also organize competitions for the future, because we need reproducibility in the research results. So it's very important to develop new and accurate simulators. I see that I still have a few minutes left. So Now I will dedicate the remaining 5 minutes to the final task, which is low latency sensing. And I want to start with a BBC Nature documentary, which I find very, very inspiring. This is a very famous documentary where you see a sparrowhawk that flies through narrow gaps, slaloms among trees, and makes a little bird magically disappear. What I find fascinating is that I've been talking so far about human pilots, but actually birds are even more agile than human pilots in some certain sense. Now, it turns out that nature, animals, humans don't use frame-based cameras, but we use a different type of cameras, more event-driven cameras, if we can call them cameras, in fact. So if you look at the past 60 years of research in computer vision, this has been devoted to frame-based cameras, but I argue that they are not good enough. And this is because they suffer from high latency and also low dynamic range. There is something to say about latency, which is that latency depends on the exposure time of the camera. So in indoor-like conditions, the exposure time can be over hundreds of milliseconds, which greatly limits the achievable agility of a drone. Additionally, as I said, standard cameras also suffer from a low dynamic range, which can be reduced if you use a high dynamic range camera. However, in this case, the working principle is to take multiple pictures at different exposure times, and by doing so, you are actually increasing the latency of the system, so you don't want to do that again. So for agile behavior, we need faster sensors and faster algorithms. Now, there is a good news, which is that for a few years now, there has been a new sensor available called Event Camera that very recently, actually 1 year ago, reached finally even VGA and 1 megapixel resolution, I'm very happy to say. It's called Event Camera, and now we have 3 major camera manufacturers, Sony, Samsung, and OmniVision, that are developing massively event cameras. What is an event camera? An event camera is a sensor that measures only motion in the scene. So to understand how it works, look at the animation at the bottom right, which I'm going to animate. Imagine that you have a rotating stimulus, so a rotating disc with a black dot. An event camera has smart pixels that are all independent of each other. And every time that a single pixel detects motion, this pixel will trigger an event. So this means that the output of the event camera is thus not a stream of intensity frames, but rather a stream of asynchronous events in space and time. Now, because of his working principle, event cameras offer 4 key advantages. First of all, they have a microsecond resolution, no motion blur, a very high dynamic range, actually up to 8 orders of magnitude superior than standard cameras, but also they offer very low power consumption in the order of milliwatts versus watts of standard cameras. But there is a problem. The problem is that because the output is asynchronous, traditional vision algorithms cannot be used, which basically pushes us researchers to come up with new algorithms to fully exploit this revolutionary sensor. Now, I will not go into the details to explain how we model mathematically the sensor because we have a survey paper on this, but I want to show for the remaining minutes some exciting opportunities for applications and research. So let's talk about SLAM. Since my former background is SLAM, simultaneous localization and mapping, we wrote a paper 2 years ago with Anthony Rossignol Vidal, which is called Ultimate SLAM, where it was a provocative title, but actually the underlying idea was to show that by using this exceptional sensor, we would unlock scenarios that are currently not accessible to standard cameras. For example, high speed and high dynamic range scenarios. And to show that, we picked a very landmark example. What you are gonna see in this video is my student spinning a camera, an event camera as well as a standard camera, as a cowboy. So basically he's holding the USB cable of the camera that was very well fixed, of course, and then you're gonna see that the standard frames are gonna be affected by motion blur and also, you know, very high abrupt changes of illumination. But so the performance of SLAM is going to be strongly impacted. You cannot extract features, neither track them and perform a trajectory estimation. On the other side, thanks to the amazing properties of the event camera, you can see on the right that the image is different, it looks different, but it's sharp. and we can extract special features, event corners, we can track them, and then we can use them to run standard backends. So now the video. So this is the performance of Ultimate Slam in real time. It runs even on board an Odroid, actually, not even a Jetson. I mean, much poorer than a Jetson in that sense. It runs in real time. It can also cope with this very agile motion. So the natural application of this was now to apply to a very relevant problem for robotics, which is safety. This is actually unpublished work. We just submitted it to RAL, which is autonomous quadrotor flight despite rotor failure. This is actually something that is very relevant to us, especially in Zurich, because as you know, in Switzerland, we have already had more than 4,000 autonomous flights, all with GPS, operated by Matternet and the Swiss Post. And last year, we had one crash caused by a rotor failure. So the drone went down and it fell 50 meters away from a kindergarten where children were playing. Now, you know, there has been work done by Raffaello Andrea and De Visser from TU Delft on trying to build controllers that can take over when a single rotor completely fails, so that of course the quadrotor will start spinning on itself, but you can actually control it so that it doesn't fly crazily away and it doesn't crash. However, to do that, you need a very accurate, reliable position estimates. And what they showed in those works is that they were using either Vicon, so motion capture, or GPS. What we show in this work is that now we can finally do it with onboard sensing and computation thanks to the event camera. So let me go to the video. So you see here the quadrotor. We stopped one rotor. So now it's only using the other three. And actually the co-authors of these are De Visser and a species student who was visiting me. You see on the bottom left, what a standard camera would see, super motion blurred. You cannot do anything, so the drone will crash. Here you see the events in the middle, the event frames, where basically we extract features, we track them, and then we can reliably do state estimation thanks to Ultimate Slam. So we finally were able to show that we can actually do this, solve this problem. Here we also show that we can follow a given trajectory. I'm about to close. Another application I want to show is very recent work on low latency, high bandwidth control. Do you know those YouTube videos where you see a chicken moving in front of the mirror, and then if you move the chicken, the head remains stable? So it's as perfect as, how's it called, a steady controller, camera stabilizers. So here we try to do something similar by using a dual copter. So the dual copter is constrained to rotate around an axis parallel to the optical axis of the camera. So we have an event camera installed here. This is a dual copter with the two propellers. And we are trying to mimic the rotation of this disk. So my student is gonna rotate the disk. And what we want to see is if, thanks to the low latency of the event camera, we can actually mimic the behavior of the passive disk with no perceivable latency. Let's see. I hope it plays. This pretty aggressive, actually. So I don't know if it plays well, smoothly in Zoom. But there is some latency, but it's actually due only to the time constant of the actuators and to the inertia of the system, by the way. Because here, actually, the state update comes at 1000 Hertz. And we have an event-based out-transform that does the line detection. Now, where are we going? Where do we want to go? We applied this low latency control to the task of dynamic obstacle avoidance, where we showed, and this was a science robotics paper that appeared this year, that for the first time we could actually avoid objects aggressively thrown to a quadrotor while the quadrotor was actually moving. We show in this paper that we can achieve a latency, visual latency of 3.5 milliseconds, and with relative speeds between the ball and the quadrotor of up to 10 meters per second. Now, how does it work? Many people ask me, so I decided to show it. So this is actually very cool. Like you can do this with an event camera at very low latency because the event camera streams a continuous stream of information. While with standard cameras, you get only frames at constant time intervals, usually with unit space at 30 milliseconds. Now you don't need to do that because the stream of information from an event camera is continuous. But now what you can see here is the space-time signal recorded by the event camera. And what we do is that we apply a method called the contrast maximization that allows you to warp the events according to the direction of motion that generated them. And if you do that, what you get is the resulting image. It's sharp in correspondence of event static background, and it's blurry for events that were generated by the moving objects. So we have a simple algorithm to tell apart moving from static objects. So that's one of the opportunities of event cameras. We also have a pair where you can actually learn that, done in collaboration with Eileen Monos and Vermeulen from Maryland, by the way. So this takes me to the conclusion. So remember the umbrella of this talk. This talk was about autonomous vision-based agile flight as a new research topic. I believe it will take at least 10 years to solve it, if we will ever solve it, actually, for now. It's important because it raises fundamental challenges for robotics research, and also it pushes the limits of existing algorithms in extreme conditions. I also talked about the importance of tight coupling, perception, and action loops. I also talked about learning versus model-based policies, and I think that combining model-based and machine learning methods can greatly boost the performance, but the important question is what should be learned, what should be modeled. Also, I talked about event cameras, but more in general, we know that new sensors hold promise to push the performance and also bring new interesting problems to solve. By the way, we released usually a lot of code open source. We have more than 30 open source software packages released. And we also have all the slides are available on our website together with all the videos and also plenty of data sets. And I'm also, by the way, hiring postdocs in AI. And with this, I would like to thank you for your attention.
So I think while Davide reconnects and while we're waiting to ask all our questions, I can already start introducing the panel. Just a bit about logistics. If you in the audience would like to ask Davide a question, you can submit it through the Slido interface that is on our webpage, just below the live stream. And we're gonna post those questions once Davide comes back. All right, so
I'm back.
You're back, great. Perfect. So before we get started asking all our questions, let me introduce the panel. So we have Luca Carlone, Alberto Rodriguez, and myself as the organizers of the Robotics Today series. And on our student and postdoc panel, we have Benoit Landry, Shreyas Kosik, and Xingnang Shi. And I hope I didn't mangle these names. Apologies. And today, as our guest panelist, we welcome Professor Angela Schollig. Angela is an assistant professor at the University of Toronto and the Institute for Aerospace Studies, where she directs the Dynamic Systems Lab. And with her team, she conducts research at the interface of robotics, controls, and machine learning. And Angela is also an expert in aerial vehicles, so I'm sure she has many questions for Davide as well. So please, Angela, go ahead.
Hi, Davide. Hi, everyone. Thanks a lot for this fascinating talk. I mean, your pioneering work on vision-based flight is really impressive. And I mean, I know firsthand that this requires a lot of integration of not only the algorithms, but computing and hardware. And I think we all have to thank you for open sourcing a lot of your code and really contributing to advancing the field and supporting the community. So really, really impressive talk and experimental results. I start with 3 questions, and maybe I start with the more technical ones and then more the open-ended ones afterwards. I have a question. So related to your perception-aware control, have you ever considered putting the camera on a gimbal? This way you could decouple perception and flight orientation and probably outperform humans, because a human could never actually, control both the gimbal and the vehicle at the same time.
Yes, we have considered this, and it's a very good idea indeed. However, it would complicate things even further, because then you would have to make sure that at each instant of time, the relative position, the orientation of the camera with respect to the body frame of the drone, which means not only that you have a very good hand-eye calibration, extrinsic calibration, but also have a very good encoders and you can take into account for any deviation from those calibrated parameters that actually would incur in case of agile flight, because now during these very high agile maneuvers, you experience accelerations that can surpass 3 Gs. That means that even if you have a gimbal, this will actually be subject to acceleration that will distort a little bit the parameters. So that is for all these reasons, we decided to start with a rigidly attached camera. And if you look now also at products like Scadio, which is using 6 cameras, all the navigation cameras are actually rigidly attached. They only use the gimbal camera for target tracking. Okay, but of course, the gimbal camera would actually be future work.
Great. Yeah, I agree. I have another question related. You had a comment about accurate models are important, but also low latency. And so there is kind of this ambivalence. If you have a really accurate model, you can do really good at prediction, and then you can compensate for latency by prediction. So, but an accurate model may require more computation time, and prediction may require computation time. How do you trade off the kind of model accuracy and latency, or how have you dealt with this in the past?
Yes, so there are different answers depending on the task. So we are still, limited by the task, obviously. So we cannot have a general algorithm for every task. So for the task of drone racing, for example, drone racing, we exploited a modular approach rather than an end-to-end control policy. So we have a separation of estimation, planning, and control. Although the planning and control are actually fused together with the MPC, and that is also for a reason. Not only to cover perception, not only to bridge the gap between these two, but also to reduce further the latency. Now, for the task of drone racing, it's very important to have a very good understanding and model of the environment. So it is true that when you do drone racing, for example, human pilot drone racing, often the track is available beforehand. And actually, when we participated in the autonomous drone racing competition at the Alpha Pilot Challenge last year, we had a prior map. However, the prior map was not known accurately. So they said that the gates could be off by 3 meters. So you need to be able to adapt with this. Okay. Now, the problem with the models is that, okay, let's talk about perception models. So if you make an assumption about the environment and you assume that the environment is composed by a chain of gates, and these gates have a square shape, okay, what happens if, for example, you have perception problems like a lamp in the field of view of the camera? So this would happen often in those competitions, because basically most of the pixels will get washed out. And in this case, you lose a corner or a segment of the gate, and then the standard handcrafted descriptor basically would fail. And that's the reason why we opted for the end-to-end control policy. Regarding instead the other approach, acrobatic maneuvers, another reason why we wanted to opt for the end-to-end controller as opposed to the traditional architecture was to reduce the latency. So of course here we had to learn everything, but what we gained was that we reduced further the latency of the overall system compared to the separation of state estimation, planning, and control. So to answer the question, what is the trade-off? Well, the trade-off is still, first of all, manually tuned. So it's still the human that has to decide which approach works best, modular or end-to-end, and it's also very much depending on the final task that you want to solve.
Great. Now I have 2 possibly short but open-ended questions. One is in your very early slides and introduction, you said, GPS can be unreliable. Now most of your work is based on cameras in some form. What are the challenges with cameras? Where are the limitations there? I know you mentioned drift of visual odometry in one place, but yeah, will cameras be the solution?
There is no sensor that can solve them all, that can rule them all, like the Lord of the Rings. No, I mean, the reality is that, of course, cameras do not see in the dark. Well, it depends, though, right? So there are works done by Roland Siegwart, Vijay Kumar, where basically they just put a torch, also Costas Alexis for the DARPA FLA, MIT JPL, they put a torch on the quadrotors, and then they're able to see. So we have solved this problem. However, there are other problems, especially in search and rescue, which are harsh visibility conditions, like, for example, smoke, fog, and so on. So in this case, though, I mean, if the smoke is very high temperature, there is not much you can do even with thermal cameras. In this case, you can use either LiDAR or radar. But in general, the point is that, it depends on what you want to do and the time at which you want to accomplish the task. So, of course, going for smaller sensors will be able to increase the agility of the platform, because the agility of the platform is inversely proportional to the radius of the platform. So that's why I try to push on passive sensors. But of course, nothing prevents to use thermal cameras or even night cameras at some point as they're getting better.
Right. And the final question, which may also be interesting for all the grad students listening. So why don't we have delivery drones or drones in warehouses yet? Where are the open challenges? What is kind of unsolved? Where should people focus on?
Okay, so why don't we have delivery drones in warehouses? So not point-to-point outdoors, but you are
sorry, like either delivery drones, which is like this one really interesting,
I see.
application, or drones in warehouses, like indoor drones for warehouse management, inspection. I think, yeah, these are two of the applications that are really, possibly 24 hours, 7 days a week applications, right? Search and rescue is once in a while, we really need them. But then we have these application areas like delivery, where they could operate 24 hours, 7 days a week.
Yes. Okay. The quick answer to why don't we have delivery drones still outdoors is mostly due to legislation. The legislation is not the same in every country. Every country has its own rules, and we have to operate according to the rules. I mean, if we start from the United States, the FAA has approved beyond line of sight autonomous flights in certain states. And for example, finally, Matternet, which was operated for the past 4 years in Switzerland, is finally operating for the first time also in the US. I think it was in North Carolina with the UPS. In Switzerland, Switzerland has one of the most liberal and open legislations in Europe. So they've been able to authorize autonomous delivery beyond line of sight since 4 years ago. Rwanda, which has also another, very open-minded legislation, thanks to their president. So they also started the zipline autonomous delivery. Now, for what concerns indoor warehouse, I would like to mention companies like, Verity Studios from Raffaele and Andrea. This is actually has shown recently in a video, interesting results where they're able to operate their drones to scan, I guess, packages inside a warehouse, all with onboard sensors as well as external sensors like ultra-wideband localization. I think there the key challenge was to, have the best onboard state estimators. But I would say also, the miniaturization of the processing units, availability of these new drone processors from the Qualcomm Snapdragon Flight Board to the new Jetson Xavier and also Nano.
Thank you. Thank you, Angela and Davide. That was really an interesting question. So I think we're going to start picking some questions that were submitted by the audience. And Benoit, you have the first question.
Hi, Davide. Thanks for a great talk. So you showed us some amazing results, I think, with the deep acrobatics flight. We have a question from Carlos V. Asking if you could give us kind of a sense of the robustness of these trajectories with respect to, for example, wind and external disturbance. And kind of as a follow-up to that, kind of connecting that with the other work that you presented on the autonomous racing, it seemed like the domain randomization for the autonomous quad racing was kind of needed to get that robustness, but it didn't seem to be needed in kind of that second line of work where you were doing these acrobatics. Do you have a sense of why that's the case?
Okay, many questions. So let me remember everything. So the first question was about, can you repeat? I forgot.
Oh, sorry. Yeah. Just if you could get us a sense of the robustness to wind,
the robustness,
for example.
Right. So you mentioned wind. So the controller is robust against model errors. Actually, it was able to control the drone with a GoPro camera on it, so which is pretty heavy. So we added, an external load, and also wind. So we had wind while we were doing the experiments outdoors. It was not strong wind. It was about 4 to 8 miles per hour. Well, 2 to 6 miles per hour, I guess, if I remember correctly, because we checked it on the iPhone. So very strong wind, of course, will be a problem, and it will certainly be a venue for future work. But if the question is about whether the sensory model control policy was actually tested with disturbance, no. In simulation, we didn't simulate any disturbance. This is actually now work that we are doing right now. We want to characterize aerodynamic effects, and we want to do that with by learning these aerodynamic effects, and then basically we want to integrate them in our controllers. And then you had another question, I guess.
Oh, regarding, I mean, you sort of answered it, but if you think why you didn't need domain randomization, essentially, but it sounds like you didn't necessarily test maybe.
Indeed, I mentioned domain randomization for the task of drone racing, because the task for which we used the network was the perceptual task, gate detection. While I didn't mention anything for the acrobatic maneuver task. Actually, we use domain randomization, but we only randomize the thrust to weight ratio. Okay, we randomized by minus 20% up to plus 20% with respect to the nominal one. But we did not randomize other parameters, other conditions.
Okay, that's interesting. Thank you.
Mm-hmm.
Yeah, next we have a great question from Tony regarding the intermediate representations you discussed. So basically, he wants to ask, how did you guys get those intermediate representations? And should we use DNNs to get those intermediate representations? Or should we still use the classical approaches?
Yeah. Okay. So the question is whether you could also use a neural network to get the intermediate representation. Of course, you can also get a neural network to get your intermediate representation. So for the task of deep drone acrobatics, we actually used the Fisher tracks coming by default from the Intel RealSense. Okay, so no processing. We got them as they were, raw. So there is an algorithm inside the Intel RealSense, which is a classic classic KLT tracker, Lucas Canade tracker, that basically automatically extracts and produces these features as output. But of course, you could also use a neural network to produce these intermediate representations. So nothing would constrain you. It's still an intermediate representation. Okay. What we wanted to show is that by using and by training on these sensory abstractions, we were able to reduce the scene-to-real gap. Okay, and we happen to use the KLT features, but we could have also used learned KLT features. Okay, it would have been the same.
Thank you. That makes a lot of sense.
So Davide, maybe a follow-up question on this question of the representations. So on the work of drone acrobatics, right, you're doing this feature tracking, like, you know, as intermediate representation. And I had, like, you know, two small questions about low-level details, like, you know, motion blur, like, you know, with traditional features, you will not get around motion blur. And also, like, you know, so how do you get around that? Mm-hmm. And the second question is, do you know if there is a ransack which is kind of filtering out the bad feature tracks, or are you taking the raw feature tracks?
Okay. So we had no motion blur in those. So the Intel RealSense, we tested, we visually inspected the data, both indoors and outdoors, and we didn't see motion blur because, you know, motion blur depends on the distance between the robot and the structure. So you have the apparent motion is maximal when you are very close to the structure, when the speed, you know, to height ratios are actually, you know, very high. So this was not our problem. Then what was the other?
The ransack, like, you know, the feature ransack to get.
Okay, the point is that this Intel RealSense is a black box, right? So it's coming from Intel, so we don't know what it's doing exactly. But of course, talking to them, we understand it's basically based on KLT features. The Intel RealSense, in principle, can also give you visual inertial odometry. So it also has a backend inside, but we didn't use it. So I presume the backend will be using a ransack, or maybe the front end also. Maybe the front end is actually using ransack. This we don't know. What I can tell you though is that when we tested it when we trained it on our simulator, we provided ground to truth feature tracks, so without outliers, because in simulation we have no outliers. We know we lay features. Actually, we have this gazebo environment, which I showed in the slides, that looks like 5 planes, one ground plane and 4 orthogonal planes with some scenery from from grasses, hills, and so on. And then we just run, I think, the Harris detector and so on that. And
so
then
maybe let me ask you a broader question, like, to follow up on that. So you're essentially using a lot of byproducts or like intermediate representation, which are on the VIO side, right? You're also debiasing the MU measurements, which is a typical thing that you do in the backend, for example. And training is based on a model-based MPC, right? So at the end of the day, like, what is the advantage? Like, my curiosity is really the advantage the fact that the network is able to execute quickly the policy? It's just a computational advantage.
No, it's the drift, the state estimation drift, the main advantage, what we show there.
So you see that essentially, like, is doing a better job inside to do the back end of the VIO. And
yes, we can say that. However, now we have a follow-up work, which is to be submitted, where actually we are also trying to do obstacle avoidance. And what we show is that compared, for example, to Raptor by Xiaozhe Shen, to the work of Nick Roy or others, or Vijay Kumar, the use of the classic separation, state estimation, planning and control, we can reach speeds up to 7 meters per second, while all these baselines can only reach 3 meters per second. So the learn-to-end control policy, so in this new work, we will show that we can also do obstacle avoidance in a forest autonomously. So we can do both planning and control, not just control, and avoiding obstacles at very high speed. Basically, we achieve this speed thanks to the lower latency of the whole pipeline.
That was my next question about planning and so on. So very cool. Thanks, David.
All right. So we have a couple of questions about event cameras. And I think all of these people are asking basically what is different between an event camera and a normal camera. In particular, are you doing optical flow estimation? And how do you find correspondences between frames directly from event cameras? Furthermore, why are they better than just a usual high-speed camera?
Okay, 3 questions. So the first question is, how do we do feature extraction with event cameras?
Yes, and is it different from normal cameras?
Okay, the difference. So I should repeat the difference between normal cameras. So in normal cameras, you get frames. Every pixel at every constant interval of time streams the information. Okay, that the intensity. In event cameras, instead, pixels only trigger information if that pixel detected motion in the scene. So if I move my hand, only the pixels that detect this motion will trigger this event. So you have a much drastic reduction in bandwidth, because basically you are not wastefully sending data all the time at 50 Hertz, okay, 300,000 pixels a second. But on average, for a standard motion sequence, you would send, for example, 2000 pixels, okay, on average. So it's a much lower reduction in bandwidth. The other question was, how do you do feature extraction? Okay, that's a very good question. I mean, I didn't have time to go through that. Feature extraction, here we have different pipelines. So you can, for example, devise an event-based fast corner detector. This is actually the one we published the earliest, I think 4 years ago, where basically, if you know the fast corner detector, you look for patterns where there is, in a circular region, some pixels that are brighter or darker than the center pixel. Well, you can actually use the time information as if it was the brightness information. But nice thing is that you can do this in an incremental fashion, event by event. Okay, so you have a sliding window in time that is completely asynchronous in space and sparse asynchronous in time and sparse in space. And we show that we can actually run this much, much faster than the standard fast running on the standard images. But we also have the EKLT, which is an event-based Lucas Canada tracker, where we show that we can also adapt the standard photometric error minimization to work with event cameras. And so we can incrementally, event by event, compute the delta I intensity difference at a given candidate patch location, and then decide over time whether that is a feature or not, and it's good to track or not. There's also beautiful work done by Margarita Klee on this and others. And basically, I would say that nowadays we have a plethora of feature detectors and trackers for event cameras.
Great.
Was there another question?
Yeah, I think you mostly answered it. The last audience question in this line of thought was why, if you're only concerned about blur and latency, then high-speed cameras could potentially be used, right?
Yes, but we have to be very careful. Okay, so it depends on the task now. It's true, there are high-speed cameras like the Phantom camera that can reach 1 megahertz, 1 million frames per second at a pixel resolution of 16 by 16 pixels. However, they are pretty heavy. They weigh 1 kilogram. They need 100 watts of external illumination in order to illuminate the target, and the memory storage is limited to a few seconds. I've seen these cameras because they're used, for example, in fluid dynamics, okay? They can only record, for example, a few seconds of phenomena. We have a PAMI paper that was published at the beginning of this year, where we show that using an event camera and coupling this with a recurrent neural network, we can actually teach the network to regress intensity frames from events. And we show that we can actually render high-speed phenomena like a popping balloon, a bullet passing through a cup, and other things for which we need a very expensive high-speed camera. Now, the maximum speed at which you can render these virtual intensity frames depends on the latency of the sensor. It is true that the resolution, temporal resolution of the event camera is microseconds. However, there is a refractory period, which is the time that the transistor takes to reset the current at the top of the photodiode, and that actually can take several dozens of microseconds. So effectively, we can render phenomena up to 10,000 FPS with the current technology. However, if you ask Toby Delbruck, the inventor of the event camera, we tell you that if you invest more money, then we should have event cameras can also go much faster in terms of latency. And that's what I think now the challenge for Samsung, OmniVision, and Sony.
So David, I will a quick follow-up, but it's about the drone acrobatics and drone racing. So you always have the best videos, you have the best demos out there. My question is, what are the failure modes? What are the failure modes? What are cases in which either the acrobatics or the drone racing is struggling to succeed?
Okay. So first of all, when you say beautiful video, we crash a lot, by the way. Okay, so we at some point I would have to do a video composition of all the crashes, the beautiful, spectacular crashes. By the way, to avoid crashes, we have two ways. Now we just inaugurated a huge flying arena, which is 1,000 square meters. So we can use the Vicon as a backup pilot. We can fly up to 100 kilometers per hour there. Until then, actually, we're still using a human backup pilot. So one of my postdocs is actually a professional pilot. He happens to be. So that is very helpful. Actually, Christian was a help, or Titus, they were helping a lot in this deep acrobatic maneuvers, especially during the prototyping stage, the testing phase, where things didn't just work right, okay, because of technical issues. What are the failure modes in drone racing? There are different ones. So, okay, first of all, well, I would say that the most predominant is the perception. So here I can enlist the phenomena that we encountered, especially in the Alpha Pilot Challenge, because it was faster than the Iris Drone Challenge, given that it was a larger scale. So there, I would tell you that basically there were constantly these lumps. So the environment was pretty dark because they wanted to increase the spectacularity of the show. And so it was pretty dark. And therefore, when the lamp was actually in the field of view of the camera, there was a big halo around the gate. You couldn't see things very well. The state estimation then would actually fail. So there you need to have, actually what we were using there is a Kalman filter that would fuse information coming from the onboard visual inertial odometry, no SLAM, we didn't close loops, and also by the gate detector. So we had a gate detector, but we also, once we had found the gates, we were extracting the corners of the gates, building a map of the gates that was then bundle adjusted as well, by the way. And then by knowing the prediction where the gate should be, we would be able to then fuse this with a Kalman filter. So we had a lot of, fallback mechanisms. However, other failure modes have to do with the aerodynamic effects. So still, if you look at these videos from Alpha Pilot, we are not flying that fast. 8 meters per second is basically, how much is that? 30 kilometers per hour. So it's pretty slow compared to human pilots that can achieve 180 kilometers per hour. Now, there are interesting maneuvers, though, that when you do these acrobatic maneuvers, especially split S or hairpin, where basically you go forward and you go back almost on the same line, where basically you generate a lot of turbulent flow. And here, you know, there is no rotor drag model that can actually help you there. So you really need to, it's difficult to model these things. So you really need to learn it. That's what we are doing now there. But, you know, we didn't experience yet this effect because we were not able to really fly autonomously with this. However, now we are experiencing these effects when we fly with Vicon at those speeds, and then we realize that actually, you know, we need to compensate for that. So there is still a huge gap there, okay?
Hello, Davide. I had one last question. So you brought up the importance of using traces from the simulator in sort of bridging the sim to real gap, so that there is some sort of similarity between what we can extract in the real world versus what we can extract in the simulator. So I wanted to ask if you can touch upon sort of what happens if you're using event-based cameras, like, and the prospect of integrating these into sort of a simulator for end-to-end training, for example.
Yes, that's exactly what we are gonna do next. Actually, that's what we're gonna do next. At the moment, the research question of this deep acrobatic work was only to address whether, you know, we could find intermediate representation that would reduce the sim-to-real gap. Now we want to investigate event cameras and see also if two things: we can significantly lower the latency, as it should, but also we want to see whether they would transfer better between simulation and reality. Okay, here I already have some preliminary results. With this PAMI paper that I mentioned before, which I didn't show today, we actually learned to reconstruct in full intensity frames from events in simulation. We basically used, we have an event camera simulator that we open sourced. It was a Coral paper from 2018, where basically we really are able to really render events with a microsecond latency. And then we show that by using the simulator and training in simulation to reconstruct images. So we used, you know, grayscale, ground truth, intensity frames, and we're trying to reduce the perception loss between the prediction and the ground truth. By applying domain randomization, and I will tell you in a moment what we randomized, we were able to transfer to real event cameras and actually to 3 different event cameras. So from 3 different manufacturers. That was pretty informative for us, insightful, because it shows that basically they seemed to transfer pretty well, okay? Now I cannot conclude that they will transfer better than standard cameras because with which this work, basically what we show is that event cameras convey the same type of visual information that is available with standard camera, just faster. However, it's the varying component of the signal, so not the absolute intensity, okay? So, so I cannot answer this question directly. I think we need now, you know, to start working on it and see basically whether we will confirm what I'm telling you, that basically it should not reduce the sim-to-real gap, or there will be an advantage. I don't think there will be a reduction in the sim-to-real gap, okay? By the way, how do we reduce the sim-to-real gap in learning to predict intensity frames? We randomize the threshold of the event camera. So events are generated every time that a single pixel intensity passes by a threshold the intensity at the same pixel at the previous event. So there is a threshold. This threshold is considered typically constant by model-based state-of-the-art approaches, but it actually is not. It's very time-dependent, and it also varies across the pixels by quite a lot, actually, by up to 50%. So we had to randomize this contrast threshold in simulation. And we showed that only by doing this randomization of the contrast threshold, we were able to generalize to real event cameras, okay?
Well, that's great. I will be looking forward to the latest results coming out from that sim-to-real transfer. And with that, I think we are above time. Thank you very much, Davide, for your great talk and the time. And thank you, Angela, for joining the panel. On December 11, we'll have the last talk of the year by Professor Carlota Berry from the Rose Holman Institute of Technology, who specializes on educational mobile robotics and enhanced human-robot interfaces. So we hope that you'll join us again. And thank you very much for coming today.